video 1 of our next chapter, we will be focusing on similar shapes. Earlier we talked about congruent shapes, which meant that two shapes were exactly the same size. Similar just means what you think it probably means, that they are very similar to each other, but they might have some slightly different characteristics. So for example, if you look at all these triangles here, and you could look at this one of two ways, right? You could look at the orange triangles. They are all similar to each other, but we could also look at the green triangles going down. They are all similar to each other as well. So first, a definition. What is a similar polygon mathematically? Well, a similar polygon has to have two criteria. Okay, just like congruent polygons had to have two criteria, one of the criteria is a match for both congruent and similar shapes. And that being that the corresponding or matching angles must be congruent. Okay, so if we were talking about triangles, all three sets of angles must match up with three other sets of angles. And I'm not saying that the angles all have to be equal to each other, that they're 60, 60, 60, but if you had, let's say, boy, I don't know, a 40, a 50, and a 90 degree angle in a triangle, that another triangle must also have matching 40, 50, and 90 degree angles. Now, the one thing that's going to be different from congruent to similar shapes is their sides. In congruent polygons, the sides had to match up. But in similar polygons, they must be proportional, which means that they must have equal ratios. So all the sides we're going to be dealing with in similar polygons, we're going to be setting up ratios and finding that they have equal ratios instead of equal side lengths. So what similar polygons look like. So here's an example. I picked two pentagons. I have one pentagon here that's larger than the other. And the way I really think about similar polygons is, if you guys, maybe this is just getting older because I'm sure this movie came out before you guys were even born, but hopefully you guys have heard of the Austin Powers reference with Mike Myers movies. And there was Dr. Evil, and there was his mini-me. Well, that's how I think of similar polygons. You have the Dr. Evil shape and you have the mini-me shape, where basically they have the same characteristics. Okay, they all have, the scarred eye here. And so I kind of think of the characteristics of two people like the angles, because the angles all have to match up in both shapes. But the proportions of sides are the same, but one shape is definitely smaller than the other. So that's how I think of similar polygons. So I would say down here that pentagon ABCDE is similar to, and notice before we had congruent to symbols, now we're kind of getting rid of the equal sign, if you will, and we're just taking the squiggle on top. Okay, for you Espanol people, it is the tilde, if you will. So we're only going to use the top of the congruent sign to represent similarity. And so when we have one shape similar to the other, we call that entire thing the similarity statement, just like we had congruency statements. So in the first example, I'm saying triangle QWE is similar to triangle RTY. Now, knowing that these two triangles are already similar, that means that all the angles match up and all the sides are proportional. So what I want to do for this one is just list all the corresponding parts and check their ratios. Okay, so in terms of corresponding parts, there's two things. There's angles and there's our sides. The angles are going to be easy, right? This is where I would just write QWE, QWE, and I know that the angles must be congruent. So if I wrote QWE in that order, then I would just write the letters of the second triangle in the same order. R, T, Y. So if I wanted to mark on these, I could. Angle Q, 1 arc mark. Angle R, 1 arc mark. Angle W, 2 arc marks. Angle T, 2 arc marks. Angle E, whoa, crazy. Angle 2. Go back there. There we go. E, I could put 3 arc marks, and Y, I could put 3 arc marks. And I know those angles have to match up because the similarity statement told me that that was the order that the angles have to go in. So that would be the angle part, which is, again, always going to be the easiest. The sides, we're going to have to check. Obviously, these three sides don't match up with these three sides at all, but that's fine. Again, we had to write them as ratios. So, how do you know which side really matches up with which side? Well, I kind of look at this as a small, medium, large operation. So let me erase this to get some space here. So I'm going to set up 3 ratios, aka 3 fractions. And I'm going to go in a small, medium, large for the first triangle. So first triangle, small, medium, large. Well, the smallest side of the first triangle here is 10, and the medium is 15, and the large is 20. And for the second triangle, and it doesn't matter if you do the biggest triangle as the numerators or the biggest triangle numbers as the denominators, as long as we're consistent all the way across. And again, I'm going to go small, medium, large. So the smallest side of my second triangle, which happens to be my smaller one, is 8. The medium is 12. And the largest is 16. This is what I need to check. Okay? Is it true that all 3 of these ratios are congruent? That they are proportional? So 10/8 I could simplify. I could divide each of those by 2 and get 5/4. And 15 and 12 has a common factor of 3. And if I did that, I'd get 5/4. And 20 and 16 have a common factor of 4. And I also get 5/4. This is what we want to see happen, is that all 3 of these ratios of sides end up being the same ratio. So since all this is true, this verifies that these 2 triangles are in fact similar. Now, one thing we could also say is that the sides are in a ratio of 5:4. Okay, whatever these 3 fractions that all come out to be equal, that also represents the ratio of the side lengths. Okay, they're in a 5:4 ratio. Or if we were saying small to big, a 4:5 ratio. Second example, same thing except we don't have a picture and we don't have numbers to check. So this is going to be purely all non-numerical stuff going on here. The angles, again, will be the easiest part. And so, if I went angle D, O, and U for the first triangle, I know they all have to match up with the 3 angles in the same order that I did the first triangle, B, F, and H. So there's all my angles. Now the sides, if you think, oh, I don't have a picture, how do I know sides going on? Well, DO would be a side. So DO, notice I used the first 2 letters. So if I went and used the first 2 letters over here, that would be side BF. Now, it's not true that DO is equal to BF, but that they make up a common ratio. Okay, so DO over BF would be equal to, now let me grab a different color. Let's say I do the second and the third letters, OU with FH. So OU over FH. And then let me grab one more different color. And then I'd have to pick first and last letter with first and last letter. So side DU would be in the same ratio as BH. And so there's me listing out all the sides, all the corresponding sides. And by corresponding, again, remember we meant matching, that they matched up. So that's all I do for example 2. 3 says determine whether these triangles are similar. If so, write a similarity statement and the ratio. So, 2 things I need to check. In terms of angles, are they all, wrong symbol, are they all congruent? And sides, I need to check, are they all proportional? Okay, so those are the 2 things I'm going to have to do. Again, the angles will be the easiest thing to do. Are all 3 sets of angles of triangle XYZ, do they match up with all 3 angles of DEF? And yeah, I mean, look, X and D, they're equal because they have the same arc marks. Y and E are equal because they have the same arc marks. And Z and F are equal because they have the same arc marks. Sweet, all 3 sets of angles match up. So the angles are good. So I could just quickly write out here those 3 statements. And I could kind of clump them together and say that all corresponding sets of angles are congruent. So that takes care of part 1, checking the angles. Now, part 2, I'll put part 2 down here, checking the sides. So again, we're going to do the same thing like we did with example 1. Okay, so I'm going to say, left triangle, and I'm going to go small, medium, large. And I'm going to set up my 3 ratios for the sides, and then I'll have the right triangle, small, medium, large. So left triangle, which I'm really talking about x, y, z over here, the smallest side is 6, the medium is 8, the largest is 12. Okay, let's do the same thing with the right triangle, not as in right-angled triangle. And we'd have what? 9, 12, 18. So here's what I need to check. I need to check, are all 3 of these fractions really equivalent to the same fraction, the same ratio? If so, then adding to it that all sets of corresponding angles are congruent, I really do have similar triangles. So let me clear this out in here. And let's see what all 3 of our fractions end up being. Well, 6 and 9 both have a common factor of 3, and I would get 2/3. And 8 and 12 have a common factor of 4, and I would get 2/3. So far so good. Those are a match. And 12 and 18 both have a common factor of 6, and I would get 2/3. So this is telling me all corresponding sets of sides are not congruent, but proportional. So really, taking this with this, I can say triangle XYZ is similar to triangle. And if I did XYZ, notice I have 1 arc mark, 2 arc mark, 3 arc marks. Then I'd have to go DEF to complete the same 1 arc mark, 2 arc mark, 3 arc marks. So there's my similarity statement. Now the ratio. The ratio, again, is where we came down and said it's really these numbers down here. Now, is it a 2:3 ratio or a 3:2 ratio? It depends on how we write our similarity statement. Since I used XYZ and it was the smaller triangle, I would say this is in a, and here's where I can use a colon to represent the ratio, it's in a 2:3 side ratio. Okay. Now, if I said 3:2 ratio, then technically I would have need to have written my similarity statement the other way around. So if I had said triangle DEF is similar to triangle XYZ, then I would say it has a ratio of 3:2. So it is important which way the numbers go in the ratio. Make sure that your smaller triangle matches up with the smaller number. All right, example 4. It says triangle ADE, which is the little guy down here, is similar to triangle ABC, which is our big triangle. Calculate AD and DE. Okay, so we're missing 2 side lengths here, AD. So here's AD, so there's one piece we need. And DE, which is this piece. Okay, so let's call AD, let's call it X, and let's call DE Y. Okay, so if I were going here, and if I wanted to solve for X first, I'm going to go ahead and throw down my X. Now, X, which was AD, well, that's the first 2 letters of the smaller triangle's similarity statement, right? Which means its corresponding or matching side would have to be AB in the bigger triangle. Well, how long is AB? AB is 12. So I know that X and the 12 go together in the same ratio. Now, I need to find another ratio that I know both numbers to. And if you compare these sides, you can see, hey, look, I know both of those numbers, the 6 and the 24. Versus if I looked at these sides, I don't know this one. So I don't want to use those because I would end up with 2 unknowns. So AE, different color, AE is the first and last, and it's 6. And AC is 24. Now notice X came from triangle ADE, and the 6 came from ADE. Notice they're both in the same position of these 2 ratios. They're both in the numerators. Do they have to be in the numerators? No. They could be both in the denominators. But you got to be consistent. They're either both in the numerators or both in the denominators. You can't switch one in the numerator and one in the denominator. Otherwise, your sides aren't truly being proportional. And the 12 and the 24, notice both came from the same triangle, triangle ABC. All right. So now we've got this guy here, x over 12 equals 6 over 24. Well, if you think back, and I think you could easily remember back to Algebra 1, how would we solve something like this? And if you said cross multiply, I would say you were absolutely correct. We could cross multiply this. I will also show you an alternative that sometimes works, and will definitely work in this example, just to give you an idea. So if we cross multiplied, we'd have 24x equals 6 times 12, which is 72. Divide the 24 over, and we get that x equals 3, which means AD is equal to 3. So there's one of our answers. Now, what else could you have done in this scenario besides cross multiply, you might ask? Well, you could just go, all right, well, 12 to 24, I'd really multiply by 2. So I'd have to take x and multiply it by the same value, 2 here, to get 6. So what times 2 is 6? Oh, well, that would be 3. Okay? You could do it that way. You know, sometimes you can easily do it in your head, but as long as you have it set up and you have the answer, and as long as it's an easy thing that you could easily do in your head, you don't really have to do the cross multiplication. All right, for the other one, DE. So I'm going to go ahead and write DE, which was y. Now DE, if I go look at my similarity statement, that was the last two letters. So I match it up with the last two letters of the other triangle, which is BC, which is the 20 here. So the y and the 20 have to go in the same ratio. Again, it could be 20 over y, as long as I'm consistent about how I'm setting up my ratios. Now again, I need another ratio where I know both numbers to. So why not just recycle the 6 over 24 down here? Now you might ask, could I use 3 over 12 instead of 6 over 24? You absolutely could. 3 and 12 are smaller numbers than 6 and 24. And you'll notice that 3 and 12 is really half of the 6 and the 24. So really they are the same ratio, a 1 to 4 ratio. So it doesn't really matter. Now here's where you might try to do your little shortcut here and go, all right, well 20 times what would be 24? Oh, that's not really a whole number. I don't know, it's 1 point something, I have no idea. So here's where you might want to cross multiply. And we get 24y equals 20 times 6 is 120. Divide the 24 over, and we get that y equals 5, which means DE is 5. And so there's our two answers. So there's going to be a lot of cross multiplication in this chapter. The last problem I want you guys to do on your own. I've told you these two triangles are similar, and you might ask, which two triangles are we talking about? We're talking about obviously this little guy right here, and we're talking about its big brother lurking in the shadows. So those two triangles are similar to each other, which means their sides are proportional. So I'm going to let you guys tackle this one. This one there's a little bit more than meets the eye on this one. Okay, so I'm telling you, it's not as simple as what you might think it initially is. So we'll go over this one tomorrow in class. And that's all.